If you look closely at two biological systems operating in perfect synchronization, you might assume they are driven by the exact same internal mechanics. But identical outward behavior often masks entirely different biological realities. Consider a classic late sleep phenotype. Clinically, this is someone who consistently reaches the midpoint of their sleep cycle at roughly 4:18 a.m. This visualization shows actigraphy recordings from two different subjects. Side by side, their sleep onset and mid-sleep timing align perfectly. From a purely observational standpoint, they have the exact same sleep schedule. Systems biology describes this as phenotypic degeneracy, the principle that a single identical end-state behavior can be produced by a combination of mathematically distinct parameters. Because their underlying parameters differ, prescribing a single, standard clinical intervention based solely on their shared sleep schedule guarantees a mathematical failure for at least one of these two individuals. To treat the actual cause, we have to separate the two opposing forces that dictate when we sleep. The first force is endogenous physiology. This refers to the intrinsic pacing of your biological clock. Specifically, it is the natural period of the suprachiasmatic nucleus, which governs how far an individual naturally drifts away from a rigid 24-hour cycle. The second force is the exogenous environment. This is driven entirely by the timing, duration, and intensity of retinal light exposure. This block diagram outlines the Homeostatic-Circadian-Light model, or HCL. A recent study by Skeldon and colleagues uses this mathematical framework to explicitly isolate those internal and external variables. By ingesting raw longitudinal light data collected from standard commercial wearables, the HCL model decouples a subject's intrinsic physiological clock from their environmental light habits. Most neurological models of sleep are computationally dense, but the HCL model strips this biology down to a highly efficient system of four ordinary differential equations. This graph plots the first major component, an exponential relaxation oscillator. It models homeostatic sleep pressure, represented here as h of t. The pressure rises during wakefulness toward a fixed upper asymptote, mu, and decays sharply once sleep begins. But that pressure doesn't trigger sleep statically. It interacts with a dynamic threshold. This secondary panel shows a weakly nonlinear van der Pol oscillator operating in a limit cycle. This oscillator represents the circadian pacemaker, and it dictates the exact amplitude and shape of that undulating wake-sleep threshold. Sleep onset is a mathematical intersection. It occurs at the precise moment the relaxation oscillator collides with the undulating van der Pol threshold. To understand how the outside environment influences this intersection, we have to look at how light forces the circadian oscillator. This visualization illustrates the Cronauer photoreceptor equation in action. It takes raw environmental light data, I of t, and runs it through a mathematical filter to apply a vector perturbation directly onto the van der Pol phase space. But human biology introduces a severe nonlinearity to this equation. The act of falling asleep forces the eyes closed, instantly gating the system and dropping the light input to zero. This establishes a tight feedback loop. Sleep timing physically controls your light exposure, and that light exposure dictates the timing of your future sleep. Because sleep actively gates light, circadian entrainment cannot be modeled with a simple, periodic external input. It requires a fully coupled system where the output behavior directly modifies the mathematical input. To make this clinically useful, researchers must achieve parameter identifiability. They have to find the correct physiological constants without overfitting the model. This chart illustrates parameter sensitivity. By isolating the upper asymptote, we can see that adjusting the value of mu strictly alters sleep duration while leaving the underlying phase timing intact. Conversely, increasing the intrinsic circadian period, denoted as tau c, stretches the circadian wave horizontally. This forces sleep onset to shift progressively later in the cycle. This heat map maps mu against tau c. The pairing creates a deep, clear mathematical minimum, allowing the algorithm to successfully fit these two parameters together. Extracting just these two fundamental parameters from 1 to 2 weeks of standard actigraphy data produces a personalized, computable digital twin of a patient's sleep architecture. Current consumer wearables track daily light volume, but measuring absolute lux is an inherently flawed way to predict sleep timing. This dynamic visualization charts light exposure against the pacemaker's phase response curve. It proves that the biological impact of light depends entirely on timing. Morning light speeds up the clock's velocity, while evening light actively slows it down. When we look at biological parameters in a vacuum, the correlation is weak. The endogenous parameter tau-c alone explains only 8% of the variance in an individual's mid-sleep timing. Analyzing the exogenous light metric on its own yields similarly weak results, explaining just 17% of the variance. This scatter plot shows what happens when the data runs through the coupled general linear HCL model. By combining the intrinsic period and the phase-dependent light metric, the explained variance jumps to 64%. Precise mathematical coupling of intrinsic physiology and environmental light timing is the absolute minimum requirement to solve the variance we see in human sleep phenotypes. Returning to this scatter plot, we can locate the two identical late sleepers from the beginning of the video. The model reveals their decoupled drivers. The first individual possesses a mathematically long intrinsic period. The second individual has a standard intrinsic period, but exhibits extreme sensitivity to evening light. We can run a computational intervention to observe what happens when both subjects are prescribed the exact same light modification therapy. These split-screen raster plots track a specific regimen, an absolute reduction in evening light past 6 p.m., paired with an intense 1000 lux morning light enhancement. The outcomes diverge sharply. The individual driven by environmental light responds dramatically, rapidly shifting their sleep phase. The individual driven by a long intrinsic period exhibits a highly resistant, muted response to the exact same therapy. The HCL model allows wearables to function as predictive engines, routing targeted closed-loop interventions based on the precise limits of an individual's biology.